Hello everyone. In this lecture, I will be discussing about Mealy circuits, state minimization, state assignment. In sequential circuits, there are two models depending on how the output is generated. Mealy model, Murray model. In the Mealy model, the output depends on both the present state as well as input. The structure of the Mealy model is shown in the figure. Here, the output depends on the present state as well as the input. So, the output of the sequential circuit are not synchronized with the clock because the output may change if the input changes. The state diagram of the Mealy model is shown here. The state diagram is a graphical representation of the behavior of the sequential circuit. In the state diagram, the states are represented by the circles. The transition between the states are represented by the directed lines. And the directed lines are labeled by the binary number separated by the slash. The first binary number represents the input and the second binary number represents the output. So, example of the state diagram for the Mealy model is shown here. Here, the circuit, it consists of three states, Q0, Q1, Q2. And the transition are represented by the lines. And this binary number represents input and the output. In the Murray model, the output depends only on the present state. The structure of the Murray model is shown in the figure. Here, the output is depending only on the present state. So, the output of the sequential circuit are synchronized with the clock because they depend only on the flip-flop output which are synchronized with the clock. The state diagram for the Murray model is shown in the figure. So, again here the states are represented by the circles and the directed line represents the transition between the states. In the Murray model, only the inputs are marked along the directed lines and the output are marked inside the circle along with the state. Example for the state diagram for the Murray model is shown in the figure. The circuit consists of 5 states Q0, Q1, Q2, Q3 and Q4. So here the directed lines are labeled by only one binary number which represents the input. The circle represents the state and Q1 represents the present state and 0 represents the output. And this Murray model, it requires more number of gates to represent a circuit compared to the Mealy model. So next, coming to the state reduction. This state reduction algorithm, it reduces the number of flip-flops required to implement the sequential circuit. So this state reduction, it reduces the number of states and thereby reduces the number of flip-flops. We'll define equivalent states. Two states are said to be equivalent if for each possible input they give exactly the same output as well as and they go to the same next state or to the equivalent next state. So when two states are equivalent, one of them can be removed. The procedure for the state reduction is as follows. First of all, we need to derive the state table from the given state diagram. And then from the state table, you identify the equivalent states. Then eliminate one of the equivalent state and draw the reduced state table. And repeat the procedure as long as all the equivalent states are removed. The example for the state reduction. So, we'll consider an input sequence given here starting with an initial state A. The state diagram for the given sequence is shown in the figure. So, the first step is to draw the state table. The state table, it consists of present state, next state and the output for the input X. The input X can take either logic 0 or logic 1. So, we'll start with the initial state A. So with 0 as input, the next state it is A with the output 0. And for the input 1, the next state it is B with the output 0. Now moving on to next state B. So with the B as the present state, for the input x is equal to 0, the next state it is C with the output 0. And for the input x is equal to 1, the next state is D with the output 0. Now moving on to the next state C. With 0 as input, it goes to the state A with the output 0. With 1 as the input, it goes to the state D with 0 as the output. Similarly, repeat the same process for all the remaining states D, E, F and G. So this is the state table corresponding to the given state diagram. So the next step is to identify the equivalent state. So on seeing the state table, you can observe that the state E and G, they produce the same next state A, F and here also A, F and also the same output 0, 1, here also 0, 1. So these two states are equivalent. E and G are equivalent state. So we can remove one of the states. So I am going to remove the state G. So on removing the state G, I can replace G by E. So E and G are equivalent state. So I can replace G by E. So this is the reduced state table. So I have eliminated the state G and I have replaced G with E. Now again, you check for the equivalent states. So now again, on inspecting the state table, I can find that the state D and F are having the same next state E, F and also the same output 0 and 1. So these two states are equivalent states. D and F are equivalent state. So I can remove one state. So removing F and replacing F by D, I will get the reduced state table. And again on further observing, there is no equivalent state. So I can stop at this point. So the next step is to draw the reduced state diagram. So this state diagram will consist of only 5 states. Initially there were 7 states. Now 2 states are reduced. So the reduced state table consists of 5 states. Now I will start with the initial state A. For the input 0, the next state is A with the output 0. For the input 1, the next state it is B with the output 0. Then moving on to next state B. For the input 0, the next state is C with the output 0. And for the input x is equal to 1, the next state is D with the output 0. Moving on to next state C. With the input x is equal to 0, the next state is A with the output 0. And for the input x is equal to 1, the next state is D with the output 0. Now consider the state D. With the input x is equal to 0, the next state is E with the output 0. With the input x is equal to 1, the next state is D with the output 1. And moving on to next state E. With 0 as input, it goes to the state A with the output 0. And for the input 1, it goes to the state D with the output 1. So this represents the reduced state diagram consisting of only 5 states. Then moving on to state assignment. While designing the sequential circuit, so it is always necessary to assign a unique coded binary value to the state. So this procedure we'll call it as a state assignment. So any circuit with m state, will have a code with n bits where 2 power n is greater than or equal to m. So we'll consider the previous example with 5 states A, B, C, D, E. There are 3 methods for state assignment. The first method is a simple binary method. Since there are 5 states, I need to have 3 bits. So starting from 000, I am coding it as next state as 001, C it is 010, D 011, E 100. It is a simple assignment of the states. The second method, it is using the gray code assignment. So in this method, only one bit in the code changes whenever going from one number to next. So we'll start with the initial value A. So A it is assigned as 000. So the next state will have only one bit change. So it is 001. Similarly, next state will have only one bit change. So here I will be having 011. And the next state again will have only one bit change. It is 010. Similarly, each state will have only one bit change. It is 110. One more method of assigning the state is using one hot assignment. So in this assignment, only one bit in the code will be equal to 1. All the other bits are set to be 0. So since there are 5 states, I will be using 5 bits for one hot assignment. So only one bit will be 1. All the remaining 4 bits will be equal to 0. So for the initial state A, the first LSB bit will be equal to 1. For state B, the second bit is 1. For state C, third bit is 1. State D, fourth bit is 1. For state E, fifth bit, it is 1. So these are the 3 methods for state assignment. Mostly we'll be using a state assignment which reduces the cost of the combinational circuit. In this example, I have used the simple binary state assignment. So for the reduced state table, I have just replaced the state with the binary state assignment. So states A, B, C, D, E corresponding next state values with the output. Thank you. Happy learning.